Welcome to Killer Innovations. I'm your host, Phil McKinney. We are here in the studio, and lately we've been doing a whole series of guest interviews and solo shows. We are in season 16 now, and I do appreciate all of the suggestions coming in from you, the listener, for guests that you would like to hear from. So if you have additional guests that you think you'd like to have on the show and have an opportunity to hear their story, just drop me a note at phil@killerinnovations.com, and we'll work to get that scheduled. This week, we do have a guest, and this guest is actually a follow-up to a discussion that we had, some shows ago around 3D printing. Some of you actually reached out. You know my background at HP as the CTO, in the printing business, activities at HP, but a number of you were interested in a little bit more of the, I don't know what you want to call it, the tools and techniques and the thinking behind how to think about 3D and what does it really entail, and a little bit more, kind of under the hood. So in this case, we've followed up and we've brought on the show today is Andy Roberts. Andy, thank you very much for joining us here at Killer Innovations.
Thanks, Phil.
And so, Andy, give us a little bit of background. Now, you're at Desktop Metal, so we previously had your CEO, right, by title. Is that correct?
Well, Jonah, our CTO.
CTO.
He came on, yeah.
Right. And so Jonah and I were following up post that show, and he recommended that we have you on, specifically talking about this thing that you invented called Life Parts. But before we get there, give us a little bit of background on yourself. Give us, what's your history? How did you get from where you started career-wise or your early interest to, now being in the 3D printing business?
Sure. Well, I've been in the software industry for many years. I started out at a company called Parametric Technology Corporation, which was one of the first computer-aided design companies that focused on improving the productivity of engineers. So it was the first system where you could make a change to the dimensions and all the geometry would update automatically. And that was back in the 90s that this all took place. So I've been cutting my teeth in the CAD software industry for many years. But eventually I got to the point with software of being interested in something tangible, physical.
Right.
And I have a bunch of friends who are in manufacturing companies around here. And back when Desktop Metal started, the focus was on creating a new type of manufacturing around 3D printing. And I thought this would be a really interesting way to mix software with hardware. The ability to not only create software that lets you design three-dimensional things, but then actually print them out on things like this printer behind me and have the physical parts in your hand. So that's how I ended up joining the guys here at Desktop Metal.
And it's interesting, right? Because when you think about 3D printing, there's a whole bunch of buzzwords or terms associated with that, right? Whether you call it, what do they call it? Additive manufacturing.
Additive manufacturing.
Right. It's kind of the term that HP, like to use, versus subtractive manufacturing. You start off with a block of metal and then you shave away what you don't want, and you've got the remaining part left. And I have a little bit of background in subtractive manufacturing. My father worked 48 years at Cincinnati Millicron, the old Cincinnati milling machine companies. So I grew up around CNC and lathes. I can build a part, scrape metal, as good as anybody. But I think the whole concept of additive becomes quite interesting. And we're all familiar with kind of the hobbyist plastic kind of approaches that people are using, and 3D scanning a figurine for a game, or roughing out some parts or whatever. But nowadays, the sophistication of these kinds of technologies, though, has far exceeded that to finished or near finished parts, correct?
That's correct. I mean, it's possible to get on the order of 50 microns or even less
Wow.
in resolution with these technologies. And so there's never going to be an abandonment of subtractive manufacturing or sheet metal, for example, because there are always going to be the needs to finish parts to high tolerances where you need to machine things. Well, at least that's the way we see it right now. But additive manufacturing has opened up a whole new area of creativity because it allows parts to be made in ways that you couldn't make before. So, when you're making machined parts, you have to fixture them. You can't undercut them. When you're making molded parts, you have to make sure that you can pull the mold apart and that the inserts can come out. And so you have to design the parts to do that, to
Right.
behave that way.
Yep.
Sheet metal, of course, they have to be folded in succession, so you have all kinds of constraints. Additive or 3D printing allows you to print crazy shapes that you couldn't make before. So there's a need for people to understand the constraints as well as the new freedoms so that they can take advantage of the technology. What we're doing is we're building these printers and these sintering furnaces, but we're also developing software to help people understand how to take advantage of it.
Well, and I think that's important, right? Because if you're not, as you said, right, in subtractive manufacturing, you really have to think through the process of taking a block of aluminum and cutting away in the right way in order to end up with the part. The same issues, it's not just defining the outside shape, but what happens inside that shape that supports, the underlying characteristics of the device, whether it be low weight, optimized strength, torsion, all those kinds of things. And for a lot of people jumping into 3D, if they don't come from a materials background or a manufacturing background, they're going to have a high dependency on these software tools, right?
We think so. We think that there's an opportunity to help people become informed in the requirements for making good 3D printed parts. If you go to the CAD industry, if you pick up a product like SolidWorks or Creo, these are advanced CAD tools that engineers use. There are features in there that help them make parts that are either machinable or moldable. And I think that the same type of features have to be added for 3D printing.
Well, I do too. Plus, if 3D printing really is going to unlock the future of people, the creativity of people that historically would never have thought about creating a part, right? They would try to take something off the shelf or they have to outsource that. The tools do have to get much simpler because the CAD tools are designed for mechanical engineers, not the innovator trying to come up with, he's trying to transform what's in his head into something physical.
Right. Yeah, and that is all very true. They have to become simpler. And one of the inspirations for building the software that we call live parts is that we thought that there are ways in nature that design takes place that could be applied to building this new type of parts with 3D printing, which would allow the engineer to not have to create everything explicitly the way that they have for so many decades. And instead, they could set it up and push a button, and the parts would grow kind of the way a tree grows. And that would simplify the process and allow the engineer to focus more on what are the requirements for this collection of parts, not what should the shape of the parts be.
Yeah, it was interesting because this has probably got to be 8, 9 years ago. I had a person on the show out of Canada, Toronto, I believe, professor who specialized in biomimicry, right? So you think about what can you learn from an innovation perspective of what happens in nature. So the famous one is the foot pads of geckos and how they kind of suction cup to climb walls, or the invention of Velcro, coming from the burrs of its inventor walking the field with his dogs and finding out that getting those burrs out of hair is a real problem, and it turned into Velcro. So, in many cases we think we're so good at, our own human ingenuity. In some cases, we can just kind of look around for some of those possible inspirations. And if it takes the burden off of the individual of knowing all of the typical manufacturing issues and let and use this kind of concept of nature, I think that could be a real breakthrough as far as taking the burdens off of the designers for creating some of these new parts. So, Andy, as we were going into commercial break, we talked a little bit about live parts, this invention of yours that uses nature as an inspiration for the actual manufacturing of these parts through 3D printing. So give us a little bit of background on this invention of yours.
About 12 years ago, I was actually interested in the next sort of what would be the next type of design tools for engineers. And I was literally looking out the window one day and watching the trees blow in the wind and thought, in nature, nobody designs a tree. They don't sketch the shape of it. You plant a seed and it grows and it constantly adapts as it's growing. So I started looking at how cells grow in the embryonic stage. It's called, the sort of broader topic is called morphogenesis. And I started looking at how the individual cells divide and grow, and the ball of cells that forms the embryo starts to take the form of a shape. And the big question for me was, what drives that? How does a cell detach and move around and reattach and take on a new form as going from a stem cell to being a bone cell or a liver cell? And I realized it's all done through chemicals. What happens is clusters of cells react to stimulus. It could be heat, light, force, and they produce chemicals. And the chemicals diffuse into neighboring cells using things called reaction diffusion equations. That's what causes a leopard to have spots. It's chemicals interacting with each other in the pigment. And so I started to think about the idea of a CAD tool where you would plant seed cells and they would be programmed to grow kind of the way a plant grows towards the sun. These would grow towards the regions where forces are defined. And when they reach these locations, the loads would cause the cells to feel the forces and the strains. And that would trigger chemicals to be produced and cause the organism to grow stronger. So this sort of crazy idea was initially just an idea that I kicked around for a few years. But remember, this is 12 years ago.
Right.
So what I did is I built a prototype of it, and I realized that it was creating shapes that looked kind of like bones. They were very, very strong and lightweight. And I took it to the people that I had started CAD companies with and back in the 90s. And we kicked around this idea of a new type of design tool. And I since have coined the term growth-based design. But the idea was that you would set up the environment and push a button and it would grow like a living organism. And when you were done, you could send it to a printer or a machining tool or whatever. And so the thought was, this is a great idea, but how are you going to make the parts? Because the parts come out looking kind of like this. I'll hold this up. So this is a brake pedal that has been designed using this growth-based design approach. And you can see it looks kind of like a cross between a bone and a tree branch. The problem is this would be incredibly difficult to manufacture if you were putting it on a milling machine,
Right.
or if you were trying to mold it. The same thing goes for this part. This is a part from a racing car, and it's a bracket that is mounted to the dashboard and it holds the steering column. This is a part that originally is made out of about 10 pieces of aluminum that all have to be cut and fixtured and welded. And this has been actually printed as a single part, but you can see it's got all kinds of crazy little sections inside it that would be impossible if you were going to try to mold this or machine it. So while this seemed like a cool idea, this growth-based design thing 12 years ago, the problem was we don't have a manufacturing technology to make it. So I put the idea on a shelf and went off and did other software. And then 4 years ago, Desktop Metal was founded, and I knew the founders. So I called them up and said, hey, I have this idea. And the thought was, well, let's figure out if we can actually make a printing process that can scale to production manufacturing for metal as well as other components such as carbon fiber. And if we can do that, then maybe there will be an opportunity to actually build this software that helps the engineers take advantage of this new capability, because you can print parts like this very easily on a 3D printer. And you can then put them in a furnace and get a very high quality, lightweight part, which would be impossible using any other technology.
So what's the input though? Because you have to basically communicate some form of constraint. I need these holes in these locations. It's got to be able to withstand these kinds of stresses or torque or whatever.
Right.
What's the constraint that feeds and starts, I want to call it, for lack of a better term, this growing process?
Right. Well, usually engineers start out with an assembly. Like this is a skateboard truck from a typical skateboard. And you have all sorts of parts that are working together. Some of them are machined, some of them are cast, some of them are plastic, whatever. You start out with an assembly of existing parts. And what you do is you start to designate the mating and aligning areas, the parts, the regions that have to connect to other parts. You say, this is an area that has to be filled in with this shape, and this is another area that has to be filled in with this shape. And then you might define sort of a container that the whole thing has to live within. But then what you do is you apply forces. You say, well, this little piece over here is going to be feeling the force of the road. But up here, this is going to be fixed. This is going to be connected to the rider. And what we do then is essentially send all of this information to this new system. And when the seed cells are planted on the fixed areas and they grow to the areas that have forces, it's all of the boundary conditions like the fill-in areas and the keep-out areas and the fixed regions and the forced regions. Those define the constraints. So you also have to specify the material. You might say this is made out of nylon, or this is made out of carbon fiber or stainless steel. And that defines the strength of the material. So as it's growing, it knows that if the stresses are being exceeded, that it should build up more material there. Or if it has a lot of extra material, it knows to kill the cells in those regions so that it will become lighter weight. And so when you do that, you end up with a part like this, where you can see that this piece in the middle here is all hollowed out. And that's because it was grown, unlike the part above it, which is a piece that was cast. So this one has a lot of extra material, unnecessary, whereas the one on the bottom is all hollowed out and optimized for weight and strength.
Is it optimized for eliminating where I don't need it? Meaning I don't need all that extra material because I'm not casting it, I'm not milling it, I'm not machining it. Is it prioritized on strength? Are there a set of criteria? Some are more important than others. I'm assuming strength would be the one that you definitely want to focus on, correct?
Right. Sort of the most important constraints are obviously the physical ones. You can't have the part dragging on the ground.
Right.
It's a skateboard. So you have your keep out zones. Then you have your material requirements. So if it's got to be made out of aluminum, then you know that. And then you have your physical things like the forces that it's going to be subjected to. But we can get into this later. There are also manufacturing constraints. Sometimes you need to define constraints that limit how it can be made.
Yep. We talked about this video, and I'm going to start this video now, and then I'm going to invite Andy to kind of walk us through it and give us what we're seeing here. So let's get this video started. There we go. So what are we seeing here?
Here we're looking at this skateboard that I was talking about before, and right now you're seeing live parts running it. It's growing. I made the video at about 5 times actual speed, so it's a little bit speeded up, but this is running on a machine that has 3,000 GPU cores, which makes it run in real time. This happened very quickly, but what you saw was the part grow to fill in the regions that connected it to the forced and the fixed regions of the part. And now it's going through a process of adapting. So cells are being killed off and new cells are being spawned. And the color is showing you the amount of, now it's showing you the displacement of the final part, which is sometimes important if you want to make a part very stiff. And then when we go back to the beginning, you can see the part back in the assembly. And so the round trip is that you start out with the design in the CAD environment with the requirements. You go to this environment which simulates the growing of parts in a multi-physics environment, and this is where the parts are essentially geometrically formed and then exported back into the design world. What's happening here is it's unlike traditional computer-aided design where somebody designs a part and then sends it into an analysis tool to find out where it would break, and then takes the results back and has to optimize it or change it. What's happening here is the the analysis is taking place continuously as the part grows. So you're combining the design and the analysis function into one step, which if you think about it, that's what's happening in nature. Again, there's nobody is analyzing a tree to see if the hurricane is going to rip the branch off of it. It either happens or it doesn't, and then the tree becomes stronger over time in order to withstand the constantly changing environment.
Yeah, I mean, and it's interesting, in that video, watching it actually go through the grow process. Now, you said that was 5 times faster. How long did it actually take, the time that you defined the constraint, until the work was done, meaning you then were ready to send a file over to have it 3D printed?
That took about 2.5 minutes to grow.
Oh.
And at the end of that, it was able to withstand all of the finite element analysis for stress and strain and displacement. So it's very fast. Now, if you ramp that up to many parts, you can get to be instead of minutes, you can get up to dozens of minutes. But it's orders of magnitude faster than anything in the past, and that's because we're using GPUs. So these are NVIDIA's graphics processors that they developed them for gaming, right? We hijack these gaming cards that used to be many thousands of dollars, but now are almost commonplace if you go out and buy a gaming laptop, and we're using them for engineering purposes.
And is it how many? I'm trying to remember, how many GPUs did you use to do that particular part for the skateboard?
That was on an RTX 2070, I think, or 2080, which is about 3,000 cores.
Right.
So that sounds like a scary number, but we've actually run these on machines that have 10,000 cores. Companies like AMD and NVIDIA seem to be doing Moore's law at an increasing rate than it used to be.
Right.
When it comes to GPU power.
But I mean, in effect, a designer can take advantage of a workstation that they have access to. That doesn't require, you don't have to connect to Urbana, Illinois U of I supercomputer center to run these kinds of tools, right?
That's right. Well, so initially when we released live parts 2 years ago, we did find that engineers typically didn't have enough GPU horsepower, and we hosted these in the cloud. And so we're finding now that as people buy out the next generation of their computer-aided design workstations, these are things that they would run traditional computer-aided design software on their desktop. These machines have the horsepower to do it. So
right.
we're starting to make that as an option available to people that want to run it on their own machine. And it's no longer the case where you get up and go to lunch in order to wait for the operation to finish. You can literally watch it happen before your eyes. And in fact, you can change the material or change the forces while it's growing and see it adapt. So it's truly interactive.
So I think the question around this kind of grow process and the fact that you can change different constraints, how different does a part look like if it's radically different materials, say aluminum versus carbon fiber, when it does the calculation? Is it widely different, or is it just little bits of changes based on the understanding of the material?
No, the parts can be wildly different, especially if you're talking about the differences between like an aluminum versus a tool steel or a carbon fiber.
Right.
And so those are trade-offs that engineers have to make. They can look at it and say, wow, if it's aluminum, it's going to be too big or whatever, and they can change the material while it's growing and see how it adapts.
Well, that's interesting because the mechanical engineers never had that ability to really understand that before, at least not in any kind of a near real-time basis. Someone go build the part and take a look at it and go, oh, that's not going to work. We got to think of something different.
Well, the whole thing is rather crazy for engineers to get used to it first. In fact, we even have tools in the product, like we have a cell knife. You can go in and surgically slice the part, and the thing, feels the pain and reacts. The cells are literally modeled as living organisms, and they have a life cycle. They grow, they live, they die. It's a whole collection of them. And it can be extended almost infinitely in different ways. Like if we wanted to plug in heat simulation, we could theoretically grow heat sinks, because just like a part responds to forces, it could respond to heat buildup, and that could cause cells to die and create cavities, kind of like a coral reef or something. So
Well,
it is truly a multi-physics dynamic environment that can be extended to different types of requirements.
well, I love the concept of the fact that you could go in there and tweak it or cut out a portion of it, and that the part reacts, right. I'm imagining the point where the part looks at the engineer and goes, "No, stupid, you can't do that, because if you do that,
Well,
this
we
fails
could
over
do that
here."
if we wanted to. We could have it. We could have guns and shoot at it and see the blood splatter if we wanted.
But I
But
think
it,
but I think what I really love about this idea, though, is you're bringing the power of nature as a tool that it's kind of hard to tap into, right? It's
it is very
historically
difficult.
everything in the past is you got to lay out the part exactly versus something use nature to augment the engineer.
Yeah, there's some interesting things though that come up. I mean, like in nature is great, but nature, there's no examples of wheels in nature. And the reason the wheel doesn't exist in nature is because that appendage has no way for blood to flow into it. So the only wheel is something actually like a calcium deposit on something that rotates. But the other thing that's difficult is that when people make parts, they like symmetry. These parts all have huge symmetry in them. So what we did in nature, you think about it, we have 2 arms, 2 eyes, but we have 1 heart. So where does the symmetry stop, and what controls that? And so we've taken some guesses, and in the case of symmetry, we model this as a chemical gradient that can die off after some distance. So within a certain distance, the cells communicate over the symmetry boundary to try to maintain symmetry, but after a certain chemical decay, the symmetry dies off. And so we're trying to figure out ways to mix what nature wants to do typically with what people want to do. We like things to be symmetrical. The other thing is, the surface of a car body is not going to be bumpy the way the surface of a bone is. And similarly, the surface of an apple has a very nice tight shape. And so we're looking at ways now to use things like pressure to guide the curvature of parts to make them more aesthetically pleasing. Again, we're trying to balance between what would happen in nature and what a person would like to see. And sometimes they're sort of at odds with each other, such as the case of symmetry.
Well, and it's interesting because when you were showing, some of the early parts before we started today's show, you look at those parts and, like you said, it looks like bones, and bones are not perfectly symmetrical as far as the internal structure. Because if I'm an engineer and I looked at your part, I'd go like, yeah, but I would have smoothed out that part. I would have made that straighter, right? But in reality, that's not how nature operates, and in some cases, there's a good rationale with that. Andy, one of the things I always like to ask guests of the show, particularly in this 4th segment, is for advice. Now, typically, it's career advice. People who've had a highly successful career. You've obviously had a very successful career, but I'm going to ask for a slightly different advice to share with our listeners, and that is there's a lot of interest in the innovator space around taking advantage of any tools and techniques to do rapid prototyping, get those ideas out of your head into something that is tangible, that you can go test to see if the market likes your idea. But many of the innovators may have the idea, but they don't have a mechanical background. They don't have familiarity with 3D printing. What advice would you give the listener who's maybe thinking about, after hearing what you guys have been working on, for their ideas? But what should they be thinking about? What things should they consider when considering 3D printing as an option for their work, their ideas?
The 3D printing is a new technology that is still evolving, and I think that the best advice would be to get your feet wet using it in some capacity. So if you're working at an organization that has access to printing machines, whether they be plastic or metal or other types of polymer, start using them and start to understand the benefits and the drawbacks with using the technologies. One of the common pitfalls that people find when they get into using generative design software, this idea that you just push a button and it magically builds the part for you, is that it doesn't take into consideration a lot of the manufacturing constraints that are necessary. And so it's important to start using it. Like if you're going to start using generative design software, build a part and then print it out and see how it comes out. And you may find that there are manufacturing constraints, such as the need to eliminate the number of supports that are depending on the printing process, that will affect your design. So I would suggest that you take it as an evolving space with some very powerful tools already available, such as live parts. But the whole area is exploding. You can find, if you do a search for generative design software, you'll find that there are many forms of it. And some of them are embedded inside CAD systems. Some of them are embedded inside analysis tools. Some of them are freestanding, such as live parts. They can be used as a standalone.
Yeah, one piece of advice I would give when I get pinged by listeners who are interested in 3D printing is look, you don't even have to even buy the 3D printer. There's services out there where you can just send a design file and they send you the part. If you're in a major metropolitan area, and in fact, even second tier, third tier towns and cities across the world now have maker spaces where you can go in, pay for a membership like a gym membership, and you can get access to 3D printing technologies, and they'll actually show you how to use it so you can get some familiarity with it. So it's not a big cost curve. There is this learning curve, and I think the point you were making there, Andy, about just you got to get your hands involved in this. You got to go out and create some very simple parts, and you learn through the process. But in my experience, albeit biased because coming from Hewlett Packard, it's printing heritage. The pace at which you can innovate, modify, test, reprint, allows you to accelerate your innovation efforts by orders of magnitude to the old way it had to be.
That's right. I mean, the biggest the drivers right now for 3D printing are the ability to create parts that are impossible to make otherwise. So a lot of mold parts have cooling channels inside them that can't be machined, so you can 3D print them. Another one is printing replacement parts on demand. So the ability to not maintain a huge inventory of parts, especially with the COVID crisis, it's blown up supply chains. People are worried about how they can get replacement parts. And if you can bring in 3D printing and do it in-house, you have the ability to build things a different way. And then finally, there's the design innovation where you can take advantage of making changes to parts very quickly. In fact, you can even print parts where every single instance is different because the 3D printer has no tooling. There's no molds, no fixtures that need to be manufactured in order to mass produce your parts. You can mass customize parts instead. So those are the companies that are really driving it.
Yeah, and I think it's going to be a space that is going to be very transformative. Your comment on the COVID-19 and supply chain and your ability now to where you can highly distribute the actual printing activity away from the design activity, and all you're doing is sending the digital file. It's closest thing I jokingly refer to it as being I'm a Star Trekky guy, right? Is the replicators, right? Give me my replicator, send me my file, and replicate my particular part versus needing to get it shipped to me through UPS or FedEx to get a part in my hand. So Andy, if people want to follow and track what you're doing and what Desktop Metal's doing and the tool that you invented, Live Parts, what's the best way for them to keep up with what's going on?
I would say you go to desktopmetal.com. We have links that'll show you the printers, but also the Live Parts software. But if you just go to Google or another search engine and type in Live Parts generative design, we've put out many different videos. And well, I wouldn't say many. It's a very new space, but there are videos and links to articles and imagery that will show you really what it's all about.
Well, great. And we'll have all of those links up and over at Killer Innovation. So you can just hop over to the show notes and click on those links. Andy, thank you for taking the time out of joining us here at Killer Innovations today.
Thanks, Bill.
Thanks. So as we wrap up today's show, just want to remind you, if you want to be part of the community, if you want to continue the conversation of these kinds of topics that you hear on the show, or you want to tap into a community of experts, hop on over to theinnovators.community. It's where I hang out. It's free. There's no charge to it, but it's a community of innovators working on new ideas, new innovations, new concepts. And you have everything from people with very deep experience all the way to college students who are working on projects. So go check that out. And with that, we will talk to you next week. Bye-bye.